Hi, folks. I wasn't super happy with my justification for the formula for expectation in lecture. If you were there, you know. So let's talk about it again. So I'm going to observe first that the expectation of a random variable, this formula here, is just the dot product of all of the different values that the random variable can take on, the range of the random variable, with the corresponding probability that the random variable takes on that value, right? So here, when I say dot product, if you don't know that term, it just basically means take two sequences of numbers and multiply the ith term of each together, and then sum them up. Okay, so that's just another term for this process to condense these two sequences of numbers, vectors of numbers, down to a single number. In this case, it's the expectation. So the question is, why does that make sense? Why am I taking these two values and multiplying them all together and getting an expectation? Okay, so good question. Well, what is the expectation supposed to do, right? The expectation, it's taking this nice, beautiful, abstract mathematical object and it's summarizing it in this single statistic that tells you exactly what you expect on average the random variable to give you. In the messier real world, we instead have experimental averages. That's what I did in the little demo during lecture where I demonstrated doing a bunch of flips of 4 coins where you add up the number of heads each time. And when I did that, I saw that the more times I flipped the coins, the more that my experimental average seemed to converge to 2. I mean, sometimes it would get exactly to 2 and then it would stray and it would go back, but the experimental average is converging in some sense towards that 2 in the case of the 4 fair coins being flipped. So then the question is, why does this sum here converge to the expectation? Okay. Now the thing I didn't make very clear during lecture is, what does this sum mean? What are each of these pieces? Well, x1, I should make clear, is the first measurement. So when I flip the 4 coins the first time, x1 is either going to be 0, 1, 2, 3, or 4. Those are the 4 possibilities. And it is not some random quantity, it's an actual measurement. Okay. So if I do 1,365 measurements, then I would have 1,365 terms in the numerator, and there would be 0, 1, 1, 1, 0, 0, 2, 2, 2, 3, 3, 1, and so forth, right? So whatever the actual measurements are, that's what I have in the numerator here. If I add them all up and divide by n, I get some number. And what I'm trying to show you is that that experimental average, if we have a very large number of trials, is going to converge to this expectation. Okay? It's not like it's going to get locked exactly to it, but it's going to converge in some way. And so I want to talk a little more about that here and why it is the expectation, like this specific formula, that actually gives us where you converge. Why is this the end point of the real world experiment? Okay. Well, the thought experiment that I think helps us get there is to imagine if we did n experiments, so I don't know, 1,000,000, some big number n, roughly how many zeros will there be in this numerator? Right? Because some of these are 0, some of them are 1, some of them are 2s, whatever. How many 1s are there, etc.? Well, there's going to be, in that numerator, n times the probability of x equals 0, 0. So again, if I do 1,000,000 experiments, and 20% of them are zeros, because the probability of x equals 0 is 20%, then I'll expect to get around 200,000 zeros. Makes sense? It's not going to be exactly 200,000. But as n gets really, really big, if we think about the proportion that are going to be 0, it's going to be pretty close to probability of x equals 0. Okay. Now here I've just enumerated these values because I'm imagining, just as a concrete anchor in our head, the binomial random variable with 4 coin flips. But what we'll have is there's 5 different numbers that can happen in the numerator. Some of them are 0s, some of them are 1s, some of them are 4s, and some of them are 3s, and some of them are 2s, and this is how many there are. Okay. Sorry if that's a little too much. Okay. So then the next question is, if that's the number of 0s, 1s, 2s, 3s, and 4s, what is the numerator? Okay. So maybe pause this and think about it. Okay, so the numerator is just going to be n times the probability of x equals 0 times 0. Why? Because that's how many zeros you have. Okay, and at the very end, we have 4 times n times the probability that x is 4, because again, you have this many 4s. So in the numerator, you add up all those 4s and you get 4 times that number. Okay, great. So now what I've shown is that As n gets really big, this is roughly what we expect this experimental average to be. And so now we divide out the n, and what happens? Okay, the n's all cancel out, and we're left with 0 times the probability of x equals 0 plus 1 times the probability of x equals 1, all the way up to 4 times the probability that x equals 4. And I should note that that is exactly the formula for expectation for a random variable where the range is the numbers 0, 1, 2, 3, and 4. Okay. Now, more generally, if we're not just thinking about the binomial random variable, which has this specific range, if I just lop off that top term, because there's some arbitrary number of values in the range, then we still get the exact formula for expectation, right? Just now up to whatever. And in this case, we're summing over the entire range. So whatever values are possible, we're going to add up exactly this. And that, my friends, is why the experimental average actually converges to the expectation.